Hello everyone and welcome back to Indian Genes. Our very special guest today is a professor of neuroimaging and psychopharmacology at the King's College in London, where he joined in 2003 with the aim of setting up a research group focused on pharmacological neuroimaging using MRI methodology. His work was recognized and he was awarded the Young Investigator Award by the British Association for Psychopharmacology. Outside King's College, he has served on the Council for the British Association for Psychopharmacology as a member from 2011 to 2014 and meeting secretary from 2015 to 2020. I'm sure you're going to find this conversation very interesting, and I now present to you my very engaging conversation with none other than Professor Mitul Mehta. Hello Mitul and welcome to Indian Genes. It's an absolute honor and thank you very much for taking time to speak to us here on the podcast. It has been some time since we've been connecting, but here we are finally talking to each other. And why don't we get right into it and let our listeners know a little bit more about what you're currently doing, and we can take it from there.
Sure. Hi, thank you for having me. I'm a professor of neuroimaging psychopharmacology at King's College London, and I run a research group where we use brain imaging techniques to try and understand drug action. We do this for a few reasons. One is we want to know how existing drugs work in the brain, why some patients respond, some do not, which functions are affected and how they're affected. We also do this because we're interested in the methodology we use to assess brain function, and we develop new techniques. And the third reason is that we want to accelerate the development of new treatments, and we think that brain imaging could be very helpful there.
Right. And Mitul, was this always exciting for you? Because brain mapping, as it's generally categorized under, what was interesting about this and what drove you to this? Because you would have put in a lot of time, studies, hard work to specialize in this field.
Oh, yeah. So I came to it sort of indirectly. I started researching as an assistant psychologist, really not knowing where I wanted to go, but very interested in neuroscience. And I got interested in neuropsychology, which is the link between brain and behavior. The classical methods of neuropsychology are really lesion patients, so patients who have brain damage in a certain area. If you look at what they can and cannot do, you start to get clues about how different brain areas might contribute to different functions. With brain imaging, of course, you can look at the whole brain at the same time. And this is a huge leap forward. And so you can study patients who've got difficulties, but also you can study normal function. And you can understand the normal brain areas that are involved in particular tasks, how they act together, how they're connected, etc. And that was really attractive to me when I started to look at this. But also, if you give someone a drug, so drug treatments are very common in psychiatric and neurological disorders, and if you give someone a drug and you see a change in their symptoms or their behavior, that's fantastic. But what is changing in the brain that underlies those improvements? And can we use that to help understand how these drugs work and design better treatments? So they were the things that drove me initially.
And would this fall under functional imaging? Because I know that your area is broadly divided into structural imaging and functional imaging. So could you tell us at an entry level, is that a fact, and how does that breakdown work?
Yeah, so the resolution at which we scan people's brains, if you're doing a clinical study, is about 1 millimeter cubed. So you can see to that level of resolution. If you're doing research with more powerful scanners, you can get lower resolution, but it's not practical for big studies. So at that 1 millimeter resolution, you can get an idea of the grey matter and the white matter boundaries and the cerebrospinal fluid in the brain. And so you can measure brain volume in total, and you can measure brain volume locally as well in different structures, and that's fantastic. And you can look at development of the brain, you can look at neurodegeneration, the effects of learning. All these things will change brain structure. You can also measure the pathways that connect the regions, the white matter pathways, with a different imaging technique. But how about the brain when it's actually functioning and behaving, those second to second or millisecond to millisecond changes in brain activity? That's when you need functional neuroimaging. This technique, by definition, is much faster. With MRI, we use the fact that blood flow changes to areas that are more active, and we actually image the changes in blood flow or the consequences of that. The time resolution is 1 to 2 seconds, and we can look at the whole brain at the same time as well, which is a huge advantage.
Right, and this would have a direct impact, I guess, the functional imaging on cognitive psychology or things like Alzheimer's disease, right?
Oh, totally. Yeah, I mean, you can have a look at the brain systems that are associated with different cognitive processes. I think a really good example from neuroimaging comes from the literature looking at reward processing. So if your brain, or if you, and you are your brain, I suppose, if you are expecting a reward to appear, so you're playing a game, and if you press a button quickly enough, you're going to get a reward. Okay, so that period of time beforehand, when you're not actually doing anything behaviorally, you're just expecting a reward. Okay, you can look at the brain activity in that window of time when there's no behavior to observe, and you can see what brain areas are involved in this expectation process as well. So that's a really specific function you can look at, but it exemplifies the power of brain imaging because it allows you to look at brain areas that are active in the absence of a behavioral output.
Interestingly, because you said the behavioral aspect of an individual or a person, which I would like to come back to, you also mentioned some time ago about the psychiatry drugs. And what could you tell us about any of the novel drugs that actually impact a patient who is under this treatment?
Sure. So, in psychiatry, we have multiple different treatments, but the thing that's really of note is how few novel treatments have come through in recent years. So if you look at the FDA, which is the USA Drug Regulation Authority, they publish their statistics every year, and they're a very good indication of what's happening internationally. So over the last 3 years, you've got about 50 drugs being approved every year across the board. These are completely novel treatments, okay? And in the past 3 years, there's about 3 of those drugs on those lists are for psychiatry, okay? So it shows you how little novel treatment success there is. Now, why is that the case, and how can we improve it? Well, there are a multitude of reasons, but I think a big thing to note is that there is a huge disinvestment in research from the pharmaceutical industry. And there are many reasons for that, but it is difficult. Developing drugs in psychiatry is really difficult. It's not like we have something like blood pressure or a glucose level to target. And if we get a drug that changes blood pressure or changes the glucose level, then we get quite excited we're going to get somewhere and we can develop it as a treatment. What is the target in psychiatry? What's the biological target in psychiatry? That's one of the challenges. So there might be some biological targets. So the dopamine system is a good target in some disorders, like attention deficit disorder or schizophrenia, okay? But other targets like the glutamate system, which is the main neurotransmitter in the brain, that is also a good target in these disorders. But we don't have a simple marker for how that brain system isn't functioning well. It's more complex. These disorders are caused by a number of factors. Some of them might be genetic and some of them might be environmental. So it might be related to your genetics and your development and the environment you were brought up in. All of those will come together and be behind the experiences that you currently have. And so how does that look in the brain? Well, it's going to be as complex as it is. And we're starting to think about brain networks and brain circuits. So with brain imaging, what we can do is understand how certain networks might not be functioning well, and actually trying to normalize the function of those networks. That's the target. That's what we're trying to do. So instead of trying to say, right, does this drug hit this particular receptor and normalize that particular drug system in the brain, what we're asking is, does this particular drug, wherever it hits, does this particular drug influence the brain network in order to bring it back to normal? And then we can understand if it actually has a treatment benefit for the patients as well. So it's a long answer, I'm sorry. So in psychiatry, we have to remember that pretty much every treatment we have was developed before these techniques existed. So we're playing catch up big time in trying to understand the existing drugs and trying to see how brain imaging can help us with understanding new drugs. And a lot of drugs are discovered through serendipity, through good observation of clinical patients and benefits they might have that were not expected. And some of them were understood to have potential benefits because they were based on existing mechanisms that were working. But a compound that really stands out is a recent development for depression, which is the use of ketamine. Now, ketamine is a drug that was developed as an anesthetic, and it's been around since the early 1960s in clinical practice. So we understand it well. But at low doses, it seems to be an effective antidepressant. And the licenses are just being granted around the world, in the USA and in Europe and the UK. There are licenses for this drug to be used in the treatment of depression. And that's repurposed drug. That's a repurposed drug. So finding new uses for existing drugs is another mechanism that we really have not exploited in psychiatry. So that's where brain imaging can help, because we can take existing drugs and we can safely give them to participants or patients and understand what they're doing to these brain networks to try and select which drugs to push forward into bigger and more expensive studies.
And you mentioned depression and ketamine, but from your point of view, is it easier, well, nothing is easy, but is it easier for you to figure out anything to do with motor responses and how that impacts the brain and then let's say the patient, as compared to behavior? Because with the motor reflex, I guess we've got that pretty well mapped out, right? We know which motor reflex connects to which part of the brain. But when it comes to behavior, and you touched upon depression, is that a little bit more challenging for you all?
Oh, completely, yeah. So, I mean, you're right. Mapping out the systems for movement is quite well advanced. But a movement has to be initiated. There has to be an intention to move. There can also be reflexes in movement, and there'll be responses to those reflexes and learning signals as well. So understanding those other components around the actual movement is obviously quite advanced, but it indicates the complexity there. If you're looking at another critical function, such as our feelings, our emotional response to a situation, and our internal feelings about those situations, and how that affects our behavior. If you're looking at something else such as memory, or what we call executive function, these functions that basically control our behavior in certain situations, help us plan, help us organize our thoughts, etc. Yes, this is very complicated, and we really don't understand how this happens in the brain. We have clues as to which brain areas and brain networks are involved. We have some methods for studying this, but really we are at the very early stages of understanding how these more complex functions work in the brain.
And with Parkinson's disease, is that some kind of a combination between what we just spoke, because it's both motor neuron disease and leads to behavioral changes or memory loss, like you were just mentioning?
So Parkinson's disease is a fantastic example. So it's quite a devastating illness where you really characterize the diagnosis based on motor symptoms, and the cardinal motor symptoms are a shuffling gait, a tremor, and a physical rigidity. So you lose control really of fine motor movements and everyday motor movements that help you function. Now, there is a loss of dopaminergic cells in the brain, and if you replace that dopamine loss, you can have a dramatic recovery, from these motor symptoms. Now, the disease is degenerative, so unfortunately, it doesn't get better, it gets worse, and the treatment effects do not last forever. So there's a few challenges already in place, and there's a lot of work ongoing to try and overcome these challenges.
And for these sorry, please go ahead.
Oh, okay. I was going to say that that's just the first aspect of Parkinson's disease. It's a multi-system disorder. So the dopaminergic system, which is important in many functions, it's really important for movement, this is affected. But there are other neurochemical systems, including the noradrenergic system, which is involved in our attentional behavior and arousal. We've got the cholinergic system, which is very important for cognition and memory. And we've got the serotonergic system, which is really important for signaling across the brain. These systems are all affected in Parkinson's disease as well. And there are a multitude of symptoms, tongue twister there, and these include disruptions to sleep, disruptions to cognition as well. So we're beginning to understand these symptoms and that they might need different treatment approaches. But also in Parkinson's disease, we have psychiatric symptoms. So there are higher rates of depression and higher rates of psychosis in Parkinson's disease, and we're really at the early stages of understanding how we can treat those better.
And with these drugs, I guess an important part before it's tested or before it comes out into the market, how important is it for whoever is administering this to look at some part of a patient's history, or is genetics important, age and past history, or can we say that once a particular person is diagnosed with a particular illness, then that drug becomes the cure?
So I'm not a practicing neurologist, clinician, so I don't have these challenges day to day. I have research challenges day to day. Now, what do we measure? How do we measure it? But what I can tell you, though, is that no two patients are alike. Okay, so there is an old joke, I suppose, which is once you've seen two patients with a particular disease, you've seen two patients with a particular disease. And it's quite instructive, really, because it does remind you that every patient is different. Now, we can learn about a particular disorder, a particular disease, that certain treatments are definitely worth trying first. So in Parkinson's disease, no one would doubt or question that a dopaminergic replacement therapy was worth trying. But when it comes to the psychiatric symptoms and some of the behavioral symptoms like sleep disturbance, that can be more challenging, and different patients will experience these symptoms to different degrees. And so understanding their history is important. It's important because you want to know the trajectory of the disease. You want to know which symptoms appeared first. You want to know about other conditions which might cause interactions with drug treatments. But also you want to follow patients up because they might respond well to a treatment one day, but further down the line, you might need to change that treatment because their response might change. So yes, it is all important, and we're beginning to understand from an epidemiological perspective anyway, beginning to understand from these big studies which factors might be important. And I think if we understand from these big studies which factors might be important, that will ultimately help the clinician day to day to understand what sort of assessment to make and what sort of factors and outcomes to follow in order to guide their treatment and treatment changes.
And you touched on dopamine. We've been hearing a lot about it since of late, for obvious reasons, because of the consequences that it has. We were talking about attention. We were talking about people being addicted to social media, and so dopamine comes up a lot. You probably are the best person to explain to us a little bit more about dopamine. How is it naturally produced in the brain, and why does it lead to consequences that in excess in some social cases are not very friendly, right?
Sure. So dopamine is one of the modulatory neurotransmitters in the brain. So you have these fast neurotransmitters like glutamate and these inhibitory neurotransmitters, GABA, in the brain. And then you have other neurotransmitters which are called modulatory neurotransmitters, which are there a much, much lower density and concentration, but they have a big influence in modulating circuits. So dopamine is largely produced right at the base of the brain, at the top of the brain stem, really deep in your head. And the dopamine neurons project pretty much all over the brain. Okay, they project to these subcortical structures that we call the basal ganglia. Sometimes you'll hear the term striatum, which are a set of nuclei in the middle of the brain, and they're very important for reward processing. They're very important for motor function, but they're actually important for many of our behaviors, because many of our behaviors are mediated by circuits that pass through these structures. Okay, so they're involved in many, many things: decision making, memory functions, learning. Okay, you'll see these structures involved. And so dopamine gets called this reward chemical in the brain. Okay, the first thing to say is that is not true. Okay, it is true that dopamine is involved in reward processing, but it is not the reward. So, increasing dopamine isn't necessarily rewarding. So how do we know this? Well, there's some classic experiments in the 90s which recorded dopamine neurons while often monkeys were behaving in reward tasks. So they might have a certain behavior, they might press a button, and they get a reward. Okay. So what was interesting is when they learnt that you can press this button and you get a reward, when is the dopamine released? So we might think the dopamine is released when the reward is received, and there is no dopamine release when the reward is received. Okay. The dopamine is released when they press the button. Okay. So the dopamine signal is what we call a reward prediction signal. Formally, it's called a reward prediction error, because it's telling you a bit about what you expect versus what you're going to get. Okay. So this reward prediction signal, or this prediction error signal, seems to be what dopamine is involved in coding. And linking that up with the motor actions, and guiding the actions which might be rewarding, you can see that working very well and being quite useful. And you can learn which actions are the best actions and which actions are the ones to be avoided. And dopamine is involved in those learning processes, and it is well suited to do that. So what happens when you actually get the reward? What neurochemical seems to be mainly involved there? Well, that's the opiate system in the brain. So we know about opiates through things like heroin, but all these drugs act on receptors that already exist in the brain. And these sorts of pleasure signals in the brain involve the opiate system as well. So it's a more complicated set of processes, and dopamine is certainly involved, but it's not simply a shortcut for the reward itself.
And I guess because of, like you just said, the reward prediction, there is some sort of, it's a gamble. You know you're going to get a reward, you may not get a reward. Does that buy into the addiction part of a person? does a person get addicted to the reward prediction and being able to expect something? And like you said, because once it's already, you get the reward, there's no dopamine.
Sure. So, you're talking about behavioral addictions, I suppose, like gambling.
Correct.
So,
Absolutely.
yeah, excessive internet use. And certainly, there is a recognition now that there are some people who have serious difficulties in these areas. And how do we treat them? Do we help them through psychological therapies and process? Well, almost certainly we have to. But are there neurochemical understandings that can lead to sort of assistance, I suppose, with drug treatment as well? Well, maybe that will be a good outcome if we have two approaches, because not every approach will suit every person, and maybe a combined approach might even be better. But we're at the early stages of understanding the neurochemical basis of these addictions, or even the brain basis of these behaviours. So I would say that it is certainly within the realms of our understanding that the dopamine system and the opiate system will be involved in, excessive use, let's say, of the internet or problem gambling. But precisely how it's involved and how it can help develop treatments, that's research that's ongoing.
Mm. And in your current field of research, what is exciting at the moment, something that you're involved in? And could you tell us something that we've not yet read?
Oh, yeah. Well, there's a lot. So in terms of what's exciting, we're looking at novel treatments for different disorders in psychiatry. And at the moment, my group is very much involved in a few projects where we're taking a drug from a different area of medicine that gets into the brain to see what it might do in psychiatric disorders. So we do have a lot of information about the drug systems that might be involved in certain processes. So, for example, we know that across different psychiatric disorders, people experience cognitive problems. So they might have difficulties with their memory, they might have difficulties with their attention. So these are not diagnostic. These are not, for example, symptoms of the disorder that will be listed in the symptom manuals, but there's certainly difficulties that the patients will have that are recognised. And if we can improve those particular impairments, we might help these patients be able to integrate with society, with their family, and improve their everyday functioning so that they actually have a better quality of life. So we are looking at a couple of drugs, one from respiratory medicine and one from oncology, which could potentially help individuals with some of the more cognitive components of their illness syndrome. And it's early days, but the initial results we've got are very exciting, and we're really happy to push on with the next study to see if we can replicate those initial findings, if we can start to understand the brain mechanisms that might be involved, and then if we're successful there and we've got that information, then we can apply for funding to start to put these drugs into larger groups of patients to see if there's clinical benefit.
And because memory is so interesting and mainly connected to a person's inner experience, so the experience that a person has, how do you look at memory when you look at an image in the brain? How does memory strike you there? Or what are you thinking of when you're talking? I mean, memory is, from a common person's point of view, we all can experience it. But from your point of view, when you look at these images, what is memory to you?
Sure. Well, we're not very sophisticated in how we look at memory, I suppose. What we do in brain imaging is we'll give people memory tests and we'll look at their brain activity that's associated with those tests. Okay, so it's quite hard to look at the actual process of a memory forming, for example. There is some very nice research that is trying to look at that, particularly consolidation that occurs over time and overnight. But when we're doing these tests in our volunteers, we're giving people a memory test So it might be as simple as a list of words that they're reading to themselves whilst they're lying in the scanner, and we look at the brain activity associated with reading, encoding those words, really. Or we might get people to recall previous experiences or previous words, and we look at the brain activity associated with that. The critical thing, though, is what do you compare that to? I mean, the brain is active to a degree all the time. And in order to get a specific view of the areas involved in those memory processes, we need to have a control condition. We need to control for generally looking at lists of words. We need to control for lying in the scanner, following instructions, etc., etc. And we can compare that to, say, a list of words which are all the same or which are overlearned. And we can compare that to recalling words correctly versus incorrectly, for example. So these are the sorts of ways we look at memory. We look at the brain activity associated with that, and then that's the way we study memory using brain imaging.
So, Mitul, there's something I always wanted to ask, and that's about brain volume and how impactful is brain volume on either intelligence or cognitive behavior, because we do hear a lot about a bigger brain means you're more intelligent or you adapt better to your environment. Now, within individuals, is this a fact? One, is there a big difference between volumes of brain, and how do you see it?
Well, that's a great question, and there are different parts to the answer. So if we imagine a group of people who are relatively healthy and well and functioning normally in life, there'll be a difference in their brain volume. Okay, so there is a difference in brain volume between males and females. In terms of weight, male brains are on average about 1.4 kilos, female brains probably on average about 1.3, 1.25, 1.3 kilos. So already we get a difference in brain volume on average between males and females. If you look within males, there'll be a big variation in brain volume, sort of around that area though, and you look in females and there'll be a variation. So when it comes to sort of everyday functioning in this healthy, well-functioning group of people, then brain volume doesn't seem to have a big impact on people's ability and their functionality. Okay. What seems to matter, of course, is the connections in the brain, the neuronal pathways, and how the brain operates day to day, and the ability to learn. And this is not affected by those changes in volume. So if you're not well, though, and your brain volume is changing, for example, you've got a disease like Alzheimer's disease, which is reducing your brain volume, then you're losing volume that you previously had, and you lose functionality. So yeah, brain volume really matters there. And the other end of life, which is the developmental part, of course, as you're learning and growing from an infant through to a teenager and then an adult, there are increases in your total brain volume. And that seems to correlate with the changes in skills and behavior that you develop as you grow a bit older. But what's interesting about development is while you're increasing volume in those early years, you actually go through a period of time when you're losing brain volume. And that seems to be associated with improvement of function as well. So your cortical neurons might actually, so I'll just say that again.
Sure.
So you might actually lose some of your cortical neurons as you develop as well. And we understand that that is also important in order to really refine the function of brain areas and enhance our abilities as we get older as well. So you've got these two things at play. You've got the normal variation, you've got your developmental changes and the neurodegenerative changes, but there's another factor as well, which is your experiences in early life can affect your brain volume when you're an adult, and that can have an effect. So if you have really terrible experiences early in life, and we've done some research where we recruited infants who were neglected, severely neglected in their infancy, then that affects your brain volume when you're older, and that affects your functionality as well. So I can tell you about that study.
Please do.
So that is a study that was really started, I suppose, in Romania, which used to be quite a harsh communist regime, with great poverty. And during the 1980s, a lot of children were born, and the parents could not afford to look after the children. And so the orphanages started to fill up. And the orphanages were not great places. Okay, there was not much emotional contact with the orphanage staff, and also there were nutritional problems as well. When the communist regime fell and the world could see these orphanages, a lot of compassionate people looked to adopt these children into their own homes. And in the UK, there was a big effort to recruit as many of these infants as possible and their families into research and follow them up. And my colleagues at King's have done an amazing job of recruiting these infants and following them up. What we have done recently is scan as many of these individuals as possible, because they are young adults now, and what we want to do is understand how their brains now relate to their experiences when they were very young. And we can still see the effects now, even in their late 20s, after going through a really nice upbringing in what are usually very loving homes.
Wow.
And so this long-term impact is definitely worth understanding in more detail. And so, we want to do more research in this area. But certainly in this group, and the reason I'm mentioning it in relation to your question, in this group, the brain volumes were smaller. And it related to the amount of time they spent in the institutions. So the longer they spent in the institutions, the smaller their brains are now. That was in males and females. It was true of the grey matter, where the neurons are, and the white matter connections between the brain areas. And it also was related to their IQ as well. So it had an influence on their general cognitive ability as well. So, the brain volume can tell us a lot of things, but it is not a simple one-to-one relationship. So bigger is not always better.
And that means that because of the example you just cited, a person who has a lot of freedom socially, or a kid who has access to other kids through educations and schools and is being exposed to a lot of environmental, let's say pleasant environmental effects, definitely has a positive impact on the brain in that case, right? Because you spoke about a negative impact, so there must be a positive environment as well, and how that impacts the brain.
Oh, definitely, yeah. If you're being brought up in what we'd call an enriched environment, there's lots of stimulation, lots of social contact, that will have a positive effect on brain development. Now, is it a positive effect because the brain expects to have these experiences and they're important markers in normal development? Or is it a positive effect because it interacts with the normal brain development to enhance it? This is a very important question, and I would expect that both of those things are true. So the idea that we have expectations which are given to us from evolutionary development, which impact upon our brain development, I think this is well accepted. And language is a good example. So we know that in those early years, your exposure to language has a very big impact on your ability to understand and speak that language. And we know this just because people develop the language of the people around them and they learn it. And in your later years, it's much more difficult to learn other languages and learn the muscle control to accommodate the different pronunciation styles in different languages. So we have these ideas of these periods, these sensitive periods of time for development in all the brain areas. And if you miss out on those, then it will be more difficult to learn those functions as you get older. And so the environment is very important for your development. Now, your question is very good, because the question is really, how about if I can reframe your question, if you don't mind, how about the normal variations that we see? So if we go to school, we're going to have friends who might have, what we consider richer experience in their lives. Maybe their parents are better off. Maybe their parents are more engaged in their upbringing. And then you're going to have other friends where their parents might be more distant. They might experience poverty and they might have different experiences. So understanding how this normal variation impacts your development, I think is really important. We know that there are important factors in normal development. And the experiences you have do impact your brain development. They impact your mental health as well. And so understanding precisely what those factors are, precisely what the impact is, and how big those effects are, and what can be done about it, this is certainly a challenge for current and future researchers to embrace.
Because what I also was trying to get at was exactly like you said, because it has a direct impact on a lot of social policies that we have or plan moving forward. But this is not the platform or the time to get into that, where if a person has not had an equal opportunity to start, then the science is telling us that there are consequences to that. Because that person at whatever age, if he's going to compete with a person at another age, is still going to be left behind.
Oh, yes. In fact, I should be careful here. I'm a neuroscientist. I study brain function. But if you really want to impact the potential for people to succeed in life, change their environment. If you can deal with poverty, if you can deal with malnutrition, you're going to help an awful lot of people. And we know from science, from neuroscience, that these effects are really, really important. And they do affect brain development and brain function. So if you can improve these, then you're going to make a huge difference.
And I think language is another very interesting part that you were talking about, because all of us have noticed that there always seems to be a person or people who have a flair, a knack, or the ability. One is to converse fluently. The second one is to pick up different languages. That may not necessarily be connected to education, because you could see someone peaking at 17, 18, 20, whatever, and all of a sudden being able to speak continuously, influence people and have an impact. So is that something to do with a particular function of the brain? And do you all see any of that in your experiments, that some people just have that knack for language?
Sure. I mean, the ability to express yourself clearly, to coherently understand scenarios, this is a skill that people usually look up to. And it's a very impressive skill. And I'm sure that most people don't feel like they have it as much as they would like it. And
in fact, sorry, Mitul, to interrupt, but
that's all right.
On an online poll actually said that the biggest fear, and this is one of the biggest fears that people they interviewed had, was public speaking.
So one is we're talking about language development, which is probably not something we should get into now. It's a huge field of research, including multilingual language development, and trying to understand why people are very good at learning other languages, etc. And that's got to be linked with the learning abilities in the brain, but it's got to be linked also to motivation and the early life exposure that you might have as well to different languages. But the other things you're talking about are related to stress and social cognition and social stress. So this is probably what we are talking about as well. The experience of speaking in public is stressful. Okay, we can just state that as a fact, and we know that the stress hormones rise when you speak in public. We know the heart rate rises, and if you ask people how they feel on different scales, you can pick up increases in anxiety and stress, and that's completely normal. Okay, now if it occurs to the point where you cannot actually speak, then that suggests that your stress response might be too great. And we know that if you have a hyper stress response, let's call it, then that can impact the normal functioning of parts of the brain. So the front of the brain, which is involved in a lot of these executive functions I mentioned earlier, planning, organizing your thoughts, etc. If you're very stressed, then the functionality of that part of the brain can actually reduce. It can be disrupted. If you think of a sort of a natural environmental stressor that we might have encountered through evolution, and that would be a predator, being able to view a predator and respond appropriately does not require you to organize your thoughts greatly. It does not require you to be excellent at, say, calculus or something in that moment. In that moment, you need to make a very quick and clear decision about whether you stay where you are or whether you move quickly. Okay, and you need to be able to evaluate that situation rapidly, and you need to be able to respond rapidly. So when we're in a social situation and we have that response, it can appear quite dysfunctional because it can be a little inappropriate to freeze in that situation and not be able to make a clear decision because you've got this hyper stress response. But actually, it's based on a system which is evolutionary, obviously allowed us to survive to this point. So it's a really important system. And just learning how you respond to that stressful situation, what actually helps you control your stress response. They're the skills to develop and practice as well. So you can get used to the situation and you can teach your brain that even though you feel stressed, you can get through it and nothing disastrous is going to happen.
So this information that comes to you, or how you react to this in the brain, is this stored or encoded within neurons? And how does this then get changed into impulses? I'm trying to understand this particular part of it.
Sure. So you're asking actually a very big question. It's an excellent question that we're grappling with now, which is how do experiences turn into sort of learned behaviors? How do experiences turn into habits? How do your experiences actually get coded in the brain? That's the ultimate question, really. And we don't really know the answer to that. We've got brain imaging studies that give us clues. We've got cell recording studies that give us clues. We can even put probes into the brain and we could measure the sort of chemical makeup, the hormonal responses, if you like, in the brain. And that gives us very good clues. So we know which systems are probably involved. We know which systems are probably important. But actually, how does that process occur? We don't understand it very well. But you can look at what might be seen as more extreme scenarios to get clues as to what brain areas are involved. So you can look, for example, at the brain areas involved in addictive behaviors and also habits. And you can say, right, these are the brain areas that are involved when you get into these habits, these overlearned responses. So they're probably, they may be involved in addictive behaviors as well, or they may be involved when you get into habits in the early stages as well, and your behaviors are shifted slightly. So we can use these more extreme scenarios and study those to give us clues about the more everyday scenarios as well.
Because I think that also impacts the decisions we make. Because I could go left or I could go right, or I could decide what I want to do with the information that I have. And though all of us may have the same information, the processing, if the processing is influenced, then the decision is going to be influenced. I don't know if you understand what I'm trying to say.
Yeah, of course. So this allows me to talk about an area of great advance in recent years. It's an area that I'm not really expert in, but we are collaborating, and that is computational neuroscience. So if we can start to understand the factors that might be involved, in computational terms, the parameters that might be involved in the decision-making process, and the model under which that decision occurs, then we can then ask the model about what's happening, and we can look for the brain correlates of those model parameters. So let me put that in more concrete terms. So you might be, say, in a situation, in a cognitive test, where the experimenter is giving you two pictures to look at. And if you select one of the pictures, you get a reward, okay? You might get a little bit of money. And you look at the other picture, then you don't get a reward, okay? But that doesn't happen every time. There might be a probabilistic component. So if you look at the first picture, say, on every trial, you'll get a reward 7 out of 10 times. And the other picture might give you a reward 3 out of 10 times, okay? So it might take you a while to learn this, okay? And you need to, first of all, have an expectation, okay, which picture will give me a reward. At the beginning, that expectation will probably be 50-50, okay? But then you do a trial. You might look at the picture that only gives you a reward 3 out of 10 times, but you get a reward. Well, then your expectations change. You think, oh, well, maybe that other picture is the one I should be looking at. And you look at it again, and you don't get a reward. And so you might adjust your parameters a bit and your expectations a bit. So your expectations and your learning rate, these can be modeled very easily. And then you can look at the brain systems that are involved. So as we understand behavior and cognition better, we can build better models. And as we build better models, we can then understand the parameters which might be underlying the differences between people. And we can start to look at how those parameters are coded in the brain. We can start to look at how different scenarios might affect those parameters, and we can look at how different drugs might modulate those parameters. So this is a huge change in our field by combining computational neuroscience approaches with understanding of clinical disorders and cognitive approaches. Then we've got the potential to make real great advances.
And I think this is a great segue into cognitive approaches and a paper that you've just recently published that I was going through, actually, the agency and intentionality.
Yeah.
Dependent experiences of moral emotions. And I just want to read the first line here because that is what actually got my attention. It says that moral emotions are thought to influence moral behavior by providing a driving force to do good and to avoid being bad. In this study, we examined moral emotions. So, from your point of view, how did this study go and what exactly were you all trying to do?
Yeah, so, in understanding moral emotions seems like it might not be very easily available for research.
Exactly. And that was what I was thinking. Looking at the background, I was quite interested in this, especially could neuroimaging be connected to this, and is there anything to see as far as that is concerned?
Sure. So, let's first of all think about what we mean by moral emotions, okay? And I think the best way to describe it is empirically through example. So imagine you are, getting on the train or the bus, and you're sitting down, and just after you, someone gets on who might have an injury, let's say, or they might be pregnant, and you think, oh, I should give up my seat for this person, okay? What drives that decision, okay? That's a very much a moral decision, okay? And there are social norms, okay? It would be a nice thing to do in this society if I were to give up my seat for this person. But what if, for example, you had twisted your ankle really badly and actually standing was very painful, and so your decision was actually, I'm not going to give up my seat. Maybe someone else will do it, of course. What do you feel then if let's assume that you're a regular person who has these sorts of feelings and cares about the people around them in their community? Then, of course, you might feel a bit of guilt. Okay.
Yeah, I guess if it was deliberate, I'd feel more guilty.
Yeah. And then, if someone then said to you, why aren't you giving up your seat? You might feel a bit of guilt. You might feel a bit of shame, of course. You might be ashamed. And then, of course, you might explain yourself and the situation might resolve, of course. But, your motivation to explain yourself is probably coming from these emotions that you're experiencing. So we can create these scenarios through little vignettes, little cartoons, which is what we've done. And we've got many dozens of these scenarios. Some of those are, for example, in a classroom, okay, where, someone might have dropped something or broken something in the classroom, and the teacher turns around and says, who did this? And, the person that's guilty might actually stand up and say, yeah, I did it. But what if someone else said that someone else did it? Or what if you didn't do it and someone else said that you did do it? You've got all these scenarios here. You could be the victim, or you could actually be the person who's blaming someone else, okay? You're so scared of getting into trouble after you broke this glass that you point to the person next to you and said, oh, he did it, because you don't want to get into trouble. Okay, so we create these situations, and they sound a little complex. They're quite easy to understand, and they're based on everyday scenarios, okay? We give people cartoons and we give people practice. And then we ask them in those situations, if this was you, how would you feel? Would you feel shame? Would you feel guilt? Would you feel annoyed? And what we find, actually, is that we're able to understand individual differences in these moral emotions through these sorts of experimental paradigms, okay? We don't have to put the people in the situations themselves. We're able to depict the situations, and we see a strong variance in people's responses. And the way they respond, tells us that actually this is tapping into how they would normally feel as well. And then we can study this. We can study how these moral emotions relate to other factors, such as personality, such as performance on other cognitive tests as well. And we've done a study where we have been trying to explore these feelings and how they might relate to other factors as well. And actually, if we were to ask people about other factors, we call them sort of agency and intentionality, you find that they are really important factors. So the ability for you to understand that people actually have agency in their environment, the amount at which other people you think intend to, say, harm you in their behaviour, or whether you think it was an accident. These sorts of things really do affect your moral emotions in these sorts of scenarios. Yeah.
That's so interesting, because when we normally talk about morals, it's good that you actually explained what this study was all about, because I did read that first paragraph and I had the same question in my mind, because it couldn't be possible that you would, as far as the neuroimaging was concerned, you would have to look for empirical evidence, right? And
exactly. And
getting
the evidence we have here sort of aligns with other areas of psychology. No study exists in isolation, really. And that, what we've learned from this study is the better you are at taking on the perspective of someone else, the more likely you are to have a different emotional response to the situation. Okay, so if you're able to take on the perspective of someone else, for example, who might be a victim in a situation, the more shame you might feel that your actions have made someone else or got someone else in trouble or has potentially harmed someone else. And the more likely you are to be able to take those perspectives really affects the emotion you feel. And also that would tell us that if we were to extend that concept, then surely the better you are at taking other people's perspectives really suggests the better you are, the better you might be at managing these complex moral situations in everyday life. That's a question we don't know the answer to, but we like to think that having this emotional response is really a prerequisite or part of the process in taking on someone else's perspective.
Very interesting, because I think that's one of the top competencies for a leader, and the word we were getting to was empathy in what you just described. So I think that's a brilliant way of putting it. A leader with empathy is obviously going to be a better leader than a leader without empathy, whether it's in the corporate world or whether it's among small groups of people. So that is so interesting. And I just want to get
the degree of empathy is critical, and the compassion that goes with that really is what I think is important to enable you to act appropriately.
That's very deep, literally. So Mitul, could we understand the brain functions in these complex emotions and actions or empathy?
Yeah, I think we are certainly being able to do that now. Myself and other colleagues around the world are developing tasks which are able to look at the brain systems involved in things that I think many years ago we thought we couldn't really study very easily. So things such as moral emotions, empathy. We've got tasks that people do in the scanners, and we can track the brain areas that might be involved in these processes. And we can build models, just like I mentioned, about the parameters that might matter in these sorts of processes, these feelings and decisions that come with those feelings as well. So that's a great advance. And if we can start to understand, what it is that enables people to experience the emotion of someone they're watching, what is the brain area and brain areas and brain systems involved in the experience of I'm just losing myself now, sorry. I've got too many ideas. Cool. Let me just say that again, sorry.
Sure.
So we're beginning to understand how we can develop these tasks to understand the brain areas, for example, involved in empathy, or the brain areas involved in decisions which might be considered altruistic or selfish. An example is a study we've done where we've made videos of people telling short stories about scenarios they're in. And those scenarios might be positive. It might be a positive experience. They might have won something, or they might have passed an exam, or it might be a negative experience. For example, it might be the breakup of a relationship, for example, or a change in your circumstances, the loss of a job. And if we ask people to tell these stories, and we video lots of these, and we can play them back to them, and they can track for us the emotion they're feeling during this story, we can then play these stories to other people and ask them to tell us about the emotional intensity that they're feeling through the story. And what we find is that most people track the emotions really accurately. It's about just over 70% accurate when they're hearing these short stories from people they don't know about positive or negative scenarios. And then we can look at the brain and we can say, right, what are the areas of the brain that are tracking these emotions? And we know now the areas of the brain. that are involved in tracking these emotions of other people. And, you know, they're in the temporal lobe structures, including an area called the temporoparietal junction. They're in the insula. They're in the frontal lobes as well. So by having that understanding, we can start to then look at people who are not very good at feeling empathy and tracking other people's emotional responses, and have a look inside the brain when that occurs as well. So there's one example of the sorts of study you can do if you're sort of creative with your task design, and we can always get better.
And talking about tracking emotions in the brain, like the broader question here is, what are your thoughts currently on the gut-brain connection? Or is it even important in your field, and are you all considering that there is some connection there? Because it's a good saying, but is it actually happening?
Sure. Well, I don't know that mouse study. It doesn't sound very pleasant, but I can tell you that the gut-brain axis is real. And we know that what happens in the gut can influence the brain. And we know that there are certain treatments in the gut that can affect brain function. Now, the question is, what is the connection between the gut and the brain? Well, there are neurons which project, of course, sensory neurons from the gut to the brain. There are neurochemicals which can travel along some of these pathways into the brain. And we think that one of the things that really matters is what we call the inflammatory signals. So these are immune responses. And we certainly think that the immune system in the body can influence brain function. We also have responses in the brain which are immune system-like responses, which can influence brain function as well and influence the body. So we know these connections are real. That's for sure. We know these connections can have a real influence on your illnesses. So a really good example is actually in Parkinson's disease, which we talked about before. And in some patients with Parkinson's disease, they can have some gastric disorder or excess gut bacteria, not good bacteria. We've got a whole mix of bacteria in our gut. And if you can treat those gut disorders and reduce the harmful bacteria, in some patients, some of their symptoms improve. Okay, this is a really dramatic finding. How can this be? Well, we don't really understand what the mechanisms are. We know that there are connections. The connections make sense. The idea that there is an influence makes sense in terms of the physiology. How it actually happens, how big are the effects, how much control can we have over this, how much can it influence treatment? These are all very active questions in the field at the moment.
So if I sometimes say that I've made a decision because I have a gut feeling, then I'm not actually wrong.
You might not be wrong. No, you might not be wrong. You might well have a feeling in your gut. Whether that affected your decision or not is a different question altogether. So,
True. And with technology, I think CRISPR has recently been able to generate a unique genetic barcode for every single cell in a mouse's brain. So where is that taking it? And does CRISPR feature in your research as well, or are you involved with any of that technology?
So CRISPR's an amazing technology. It's effectively a gene editing tool, and it allows us to have control over certain brain areas and the genetic influences in a way that we've never had before. And what's really important is it allows us to look at causal pathways in terms of brain function. A lot of what we do in brain imaging is actually association studies. So in human studies, for example, you might be looking at the areas which are active, say, during a memory process. Okay. Now, we don't really know that the memory processes cause that brain activity. We know it's tightly linked and associated. But what we also need are studies, usually in animals as well, to accompany that, to start to look at causality. And I mainly do human research, and my colleagues are doing research in animals as well. And so CRISPR technology is potentially very important there, and it's having a big influence. But I don't do the work myself, so I haven't got any specific examples for you off the top of my head.
Okay. And I think also there was a lot of talk about electrical implants to restore either walking or help patients with paralysis. That is very exciting if that is moving forward,
Yeah.
and has such a big impact all over.
Yeah, well, that's happening. There are probably thousands of patients around the world who have electrical or electrode implants in their brains, which are improving their day-to-day functioning right now. We know that the circuits involved in, say, Parkinson's disease is a movement disorder. We know the circuits involved, and so the modelling tells us that if we were to stimulate a certain part of the circuit, we could recover what dopamine would normally be doing. We can recover that part of the circuit. And so if you get that electrode deep in the brain and you stimulate that circuit in the right way, you can recover the motor function. And that is happening right now. Deep brain stimulation is happening right now. Now, could deep brain stimulation be helpful outside of that area? Could it be helpful in severe depression? Could it be helpful in obsessive compulsive disorder, for example? It seems that the answer may be yes, but it's proving very difficult to develop a reliable strategy for treatment that passes all the important regulations we have on safety and efficacy. So a better understanding of the brain circuits involved might help understand why some people respond to these interventions, say with mood disorders or obsessive compulsive disorder, and other patients don't respond very well at all. So understanding how individual responses vary from patient to patient and how that relates to their individual variations in brain structure and function, that's a really important challenge. And we have the tools and the skills to meet those challenges now. We need the investment in the research.
And I think you covered that earlier when you spoke about motor skills. So when you're talking about deep brain simulation, this is exactly the result of that particular task. And what are your views on sticking on to deep brain stimulation? If this is a question that maybe I may divert a little bit, but I want to know your thoughts on the Neuralink and what Elon Musk is proposing.
Oh, right, Elon Musk's proposal. Yeah, I don't know the details of that proposal, but in terms of electrical activity in the brain, measuring electrical activity in the brain, understanding electrical activity during certain functions, understanding how we can modulate electrical activity with brain stimulation methods. These are all areas of research which are reasonably mature already. So I'd need to see the details, ideally in a peer-reviewed publication, to understand what he's proposing and what the contribution is beyond what we're currently doing. And if it's exciting and it's important, and then it will come through. Sure. The idea that other people are investing in good quality brain research is very exciting, but it doesn't mean that the scientific process should be short-circuited, and hopefully we won't do that.
And this is one question from me that I always wanted to know. So I'm left-handed, and I think you've already understood the question because it's very popular. And are you saying, or are you not saying, do I use the right side of my brain? And if I'm right-handed, I'm using the left side of my brain. And is it a fact that a person who uses left side of the brain, and then you have the different or various functions that go with it, is this true?
The first thing to say, Joachim, is that the idea that you've got some functions which are left brain and some which are right brain, or you might have left and right brain people, this is a myth, okay? So
you can't do this. You can't do this to me, Mitul.
Sorry, that needs to be said up front. But the idea that your right arm might be controlled more by your left-hand side of the brain, the motor cortex, and vice versa. Of course, that's true. The idea that some functions in the brain might involve the left side a bit more than the right side, This is also true. We know that, say, for example, language function largely involves the left-hand side of the brain. Or we know that when you're looking at emotional function, that the left and the right-hand side of the brain will both be active, but they might have slightly different roles. And a lot of that is because of the areas that the brains are connected to. So there is a symmetry in the brain, and the left and the right brain are very well connected together, and their activity is usually correlated as well. They're certainly not independent, but there are some sort of modular views of the brain that talk about the left-hand side might be being a bit more involved in, say, a specific emotional decision, whereas the other side of the brain might be more involved in a sort of a general emotional perspective of the situation that you're in, as just one example. So we certainly should think of the brain more like an orchestra, which is working in concert, and these modules are not discrete. And I certainly think that the idea that there are sort of more left or right hand brain people is a myth that we should quash as soon as possible at every opportunity. The idea that some people might be a bit more artistic, some people might be better at reasoning, this is absolutely fine. We don't need to invoke left and right hand brain theories for that, for sure.
So this is a big myth you're bursting here on this show, Mitul, and there has been so much of literature on it, and I guess it keeps getting recirculated. But thank you for that, and that's a big takeaway from this. People who have been promoting this left brain, right brain, spending a lot of time on articles. I think you've clarified a lot for us, and I know you have limited time, and we've got to let you go, because if you don't stop us, we won't let you go. But something that I want to touch on before we end this great conversation, and I was looking to speak to you about specifically, as you're the expert, is the debate that has been going on about whether psilocybin is ethical, whether it's even safe as a treatment for depression or mental illnesses, because I think the use of a psychedelic drug to treat anxiety or depression has to be, there has to be some medical evidence for efficiency and safety, as well as legal concerns that everyone talks about. So can you explain to us where we stand as far as psilocybin is concerned and what is safe?
Sure, of course. Yeah, this is a very exciting area of research. I mean, actually, in my own group, we have done some research with psilocybin because we think that it modulates our social cognitive abilities, social decision making, and we were able to show that it does indeed do this as well. And colleagues of mine are really at the forefront of the research into psilocybin as a therapeutic agent. So there's a few things to say here. First thing is that a drug's legal status really should not impact upon its medical utility. What should impact upon the medical utility is the medical evidence from trials. And that's what we need for all new treatments. A good example is opiates. You know, opiates like morphine, heroin. You know, we know that these are very harmful drugs if they're used recreationally. But medically, they are absolutely critical in pain management. Okay, and without these drugs, a lot more patients would suffer. So we are able already in society to balance harmful use of drugs and medical use of drugs. We already have that example. So the idea that a drug might be illegal in law but might be useful in medicine is certainly not new to us. So with psilocybin, there are many reports now of psilocybin being potentially beneficial in patients with depression. It's worth saying a couple of things. First of all, the early trials have been successful, and the stories the patients tell are very compelling. The second thing to say is that the drug isn't given alone. It's combined with therapy as well. And I think it is very important to think of these drugs like psilocybin as enabling the therapy to have more impact. That's one of the models that's being put forward at the moment. And that is at the heart of the trials that are running at the moment. It's the combination of the drugs and the therapy. And you probably don't have to give the drug many times. Maybe in some patients, you might even only need to give it once. But it's certainly not a drug that we think people will be taking every day at those therapeutic doses. And the trials are ongoing. The early indications from the open trials and some of the smaller controlled trials are very positive. But we're waiting for the bigger trials to report. And if they're also positive, then of course the licensing agencies would have to think very carefully and review the evidence to see whether licensing of these compounds in combination with therapy meets the criteria. And if it does, there's a lot of patients who could potentially benefit.
And what is informed consent when it comes down to drugs? Is that for certain drugs or a period of when a drug is being tested that informed consent?
Yeah, informed consent is a standard procedure in all human research and human research trials. Okay. The idea that the participant in the research, and that participant could be a volunteer, healthy volunteer for some research studies, or it could be a patient in other studies, they would need to be told what the study is about, what it's for, who's funding it, who's running it, what the benefits are, what the potential risks are, and what happens if something goes wrong. These are fundamental bits of information we give to all of our volunteers, all of our participants in every one of our research studies.
And I guess that would have happened with the coronavirus vaccine as well. And I don't know if you are aware, but some good news has just come out a few days ago.
Yeah, about that's very positive news. Yeah, there is some indication that this Pfizer vaccine may provide some benefit. Let's wait for the full report to come out, though, because it's only a small number of people so far. But certainly welcome the news. And there would have to be informed consent from all of those thousands of volunteers that took part in those trials, definitely.
And Mitul, before we let you go, we would just want to ask you a couple of questions to you. One is, currently, what do you find exciting in what you're doing, and where do you see this going? What are you expecting to happen over the next 10 to 15 years? What is your prediction? What is going to be a big game changer? That's one part of it. And the second part of it is, where do we find you if any of our listeners want to hear more about you, your publications? Do you plan to come up with a book that you would want to write and put together, or anything that you want to put out to all our listeners?
Well, the thing that really excites me is the experimental data. So if we're testing a drug and we're doing it in an experimental context against a placebo, and we're getting indications that this drug might actually be modulating brain function in the way that we predicted, that still excites me. That's really what it's about, that we can provide evidence for a novel approach, a novel treatment, which could potentially benefit patients. What's getting quite exciting now is that the idea of repurposing existing drugs has always been around, but it's really growing now. And now we have more technology and techniques to enable us to study the brain, to study people's clinical records, for example. We're getting more clues as to potential repurposing opportunities. And of course, the benefit of that is the rapid turnaround. You've already gone through safety testing, so you could be benefiting patients much, much quicker than with a completely novel compound. And if you want to find out more about me, you can look me up, I suppose, on any old search engine. I'm sure would find me at King's College London. I'm on Twitter as well, if you want to see what I'm tweeting about. Apologies in advance if you don't like my tweets, but they occasionally get distracted by politics, so that happens. But and also every researcher really at King's has their own webpage which lists the grants, the funding we currently have, so you get an idea of what we're currently working on. And it lists all our publications. And everything that I publish at the moment is freely available as well. So you don't have to pay for any publication. You can either get it directly from the publisher, or you can get it from the King's search portal, and you can download my publications there.
We have a lot of students who are going to be listening to this. Some of them are in school, some of them are in high school and early university. What would your guidance or advice be to them? Should they have found this interesting, or they already had an inclination to get into this field of neuroimaging and pharmacology and now have made up their mind, what do I do if I want to get into this? And could you give us some kind of guidance?
Sure. Well, I mean, guidance for everyone out there is very difficult, of course, because everyone's a bit different. But the thing I would say is find what you're interested in and start following that thread. Because you might think you're talented in one area, or you get particularly good results in one area, and if you also find the area fascinating, that's great. But it doesn't necessarily mean that you might not find other things fascinating. So find what interests you. What do you end up reading about? Where do you get lost in reading about something? And follow those areas. Because if you're interested, it will keep you motivated. And it's a long journey. There's a long career ahead of you if you want to be a scientist. And you need lots of ideas. And that's going to come from being motivated. And nothing motivates you more than a deep interest in a subject. So find what's interesting, follow that thread, and things will fall into place. That's what I'd say. And if you want to do neuroscience, even better.
So, Mitul, it's been an absolute pleasure talking to you. And we've gone well past the time that we bargained for. So thank you so much for your patience. But the amount of information we were able to gather, or the depth and width of this conversation was stunning. So thank you so much for being able to adapt to this kind of questioning, and for us it's been an absolute pleasure. We've spent our time really well. I just hope you've spent your time well as well, Mitul.
Oh yeah, thank you very much for listening to me. I really appreciate it.